Tag zusammen, heute 25. April 2024, Vorlesung Business Intelligence, WIN Wirtschaftsinformatik Semester 6 gemischt. Heute werden wir anfangen mit einem Thema, was allgegenwärtig ist. Regiert gerade die Welt der künstlichen Intelligenz. Ich fange mit den Baby Steps heute und langsam, wenn wir uns voran bewegen, wahrscheinlich nächste Woche, dass wir die Transformer-Technologie uns angucken, also den Motor von ChatGPT zum Beispiel. Okay? So, aber ich fange an mit den Baby Steps. Also heute mache ich eine Einführung in Deep Learning, die mache ich in Englisch, okay? So I will name today's lecture Deep Learning by Hand. Okay? Also we will make deep learning with a pen and a piece of paper. And you will be asked to do that in the exam as well. Okay, so you need to understand the principles here very good. Later on, to program the things on the internet, on Python or whatever, is not a real challenge. Here the challenge is to understand what's going on. Okay? So the first element that we will look at is the single neuron. It's the simplest form of, it's not even deep, it's the simplest form of learning. Okay? Single neuron perceptron. Okay? It's our first concept today. We will look at different concepts, but this is our first concept today. What happens here is that we have a series of input functions. Let's say x1, x2, xn. You can take them as the pixels, the pixel numbers on an image, or you can take them as the letters in a text, okay? Then we have some weights, where I start with 0, which is the standard way. 0, 1, and so on until n. And then we have some weights that we are going to be learning and calculating, okay? And all this is going to be added by a neuron, in which we do the add up of all these xy times wy. And with a bias. Then we have an activation function. Okay, I'll just paint a step function here. And then we have the output. And we have the calculation of an error in what we call the backpropagation process. Okay? So how does this work? Step one, so this is the perceptron neuron. Okay. Step one, we multiply all input values x, y with their corresponding weights w sub y, and then calculate the weighted sum. Okay, so basically what we do is we take the inputs, the weights, and multiply them. So step two, an activation function. I guess the bias comes later, so I will just put here what the perceptron does. An activation function is applied to the above giving us an output of the form y is the output, okay, is of the form activation function of the sum of the product plus a bias. This bias, this is the formula of this thing is the formula of a line, okay? Different tangent, this unterschiedliche Neigungen, but it's a line depending on the weight. And we add a bias. So this is the line. We add a bias to move it from the origin somewhere, okay? But it's the formula of a line. So the perceptron is nothing more than a super simple linear regression algorithm. That's the same. But it takes many inputs, which is a very good thing, okay? So it was a revolution when it was first developed. So the perceptron well, let me continue with the steps. Then after the activation function, which let me say can be of different forms. I show you some, okay? The one activation function is the step function. So basically the step function, what this function is doing is it is taking everything that is negative and makes it 0, and everything that is positive leaves it the same, makes it constant, sorry. So whatever you have in negative, it will be eliminated, and whatever is positive, it will be made constant. Okay, this is one possibility. Another possibility that works better, it's the sigmoid function, which works like this. Works better, is smoother, but because it's derivable, okay, it can be derivated close to 0, but it is very complicated to deal with. That's why we take usually in the beginning something called rectifier linear unit, or short ReLU, okay, rectifier linear unit, and it's a function that does this. Everything that is negative is brought to 0, and everything that is positive is left the same. Okay, so here is I equals x, and here I equals 0. Okay, this is the ReLU activation function. So what we do here is we are going to be calculating the error . So the step 3 is we need to calculate the weight values which make the equation E as a function of the weight and the bias as similar as possible to a prediction. Okay? In other words, we are calculating an error. Okay? And we calculate the error of a prediction y with a hood, okay, with a hat. The error is the quadratic error. It is 1 divided by 2 y minus y hat square. Okay, which is basically 1 divided by 2 y minus the sum of wi minus b. Okay? I guess I should use the hat here. That would be more accurate. Okay? Wie bitte?
Das Quadrat fehlt am Ende, oder?
Das Quadrat, ja, entschuldige. Okay? We call this error cost. Okay? And we want to find the values of W1, W2, Wn that minimize the cost. Okay? So how do you minimize such a function? The first derivative is 0. Okay? That's the minimum of a function, of a multivariate function. So the derivative of the cost to W1 is 1 divided by 2, 1 divided by 2, yes, times 2, times y minus omega 1 x1 minus W2 x2 Gesundheit minus Wn xn times minus x1. And for 2 is the same. And so on until the last. Okay. These derivatives are called gradients. Okay? So we are here. We have calculated the error. We have multiplied. Okay? We have added. We have applied the activation function. We calculate the error. What do we do now? We add it up and we adjust. Okay? So that was step 3. Step 4. Now, to reach a minima, we will start taking small steps towards the direction of the minima. Opposite direction of the gradient. So we are looking for a gradient descent. We want the gradient to be always smaller. Okay? We do so by updating the weights by a small amount each time. Okay. This small amount is called learning rate. Okay? And the way to represent this is like this. We have a cost function. Okay, and here we have a minimum, and every time we try to adapt our learning rate, our steps to reach the goal. Okay? When we have a minimum of the error, we have achieved the optimal performance. Okay? So let's do now these steps by hand. Imagine example or several examples, okay? Example number 1, single neuron perceptron forward pass. Forward pass means before going back. Okay? So only forward. And imagine I give you following data, and I can perfectly do that in the exam like this, okay? I give you following data, and I say the weight matrix is given by 1, -1, 1, and the bias is -5. This is W1, W2, W3. Okay? And I have a signal with values 2, 1, and 3. And then I tell you, please apply relu as the activation function, and give me the value that a perceptron would do in the first forward pass. How you guys do it? So here I apply relu, or better said, relu. How do we do it? You need to do the following. So this is the bias. I always like to shade out the bias. I shade it. You don't need to do it, but I recommend it. Okay? So how do we do it? This is x1, x2, x3. Simple math. x1 times w1 plus x2 times w2 plus x3 times w3 plus bias. Habt ihr Fragen oder lustiges Kommentar oder irgendwas? Passt alles? So, das ist 1 mal 2. 1 mal 2. Oder besser gesagt 2 mal 1 plus 1 mal minus 1 plus 3 mal 1 minus 5. Richtig? Also wir machen nichts anderes als 2 mal 1. Ich markiere es jetzt so mit Farben, vielleicht ist es einfacher. Und dann 3 mal 1. Okay? Und dann minus 5. If you guys do that, this goes to minus 1. So this is minus 1. But because we are applying ReLU, everything that, ReLU is a function that does 0 if x is smaller to 0, or x if x is bigger than 0. Okay? This function. Here, on the right. Because the number is minus 1, here our result is 0. And this is the result. This is the feed forward or forward pass of our single perceptron neuron. This is the first step of deep learning. Any questions? I am taking really baby steps, okay? So really super slow baby steps. But you need to come with me all along. Otherwise, I cannot. No. So, is there any questions? Do you have questions online? Hello? Do you have questions here in the lecture room? Do you have questions online?
Von meiner Seite aus nicht, ne.
Nine?
No.
Have you seen this already before? Yeah?
Yes, of course.
You have? Where?
From learning at home and from school or from university.
Where?
My master's.
Where in what? In the masters.
Yeah.
Yeah, in the masters. Yeah, most of
Yeah.
the attendees haven't seen the masters. Those in
Yeah.
bachelor, have you seen this before? Yeah, no. Where have you seen it?
No.
Yeah, in YouTube. Aber hier nicht in der Hochschule. Good. Okay, so this is the first time in the university. Good. So example number 2. Now we have not one perceptron. Now we have layer. Okay. With several nodes. Okay. So now imagine. So now is calculate the output of 2 layers of perceptrons, 3 and 4 neurons each. Okay? So now imagine I give you this. Configuration. I give you this configuration. And this, wait, I want to do it pretty. So our weight matrix and B. So, I mean, we have this. Our layer looks like this. Three and then 4. Okay. So the input values are 2, 1, and 3. And then I need to deploy them also here as well. So here we have 2, 1, and 3. Those are x1, x2, x3. Okay. And then we have a weight matrix W, and we have a bias, and the weight matrix is like this. 1, the bias -5, 1, 1, 0, 0, 0, 1, 1, 1, and 1, 0, 1, -2. Okay? And we want to calculate the output here, which shall be also, of course, a ReLU. So this is ReLU. And then for values, because we have 4 neurons. And this is going to be Y1, Y2, Y3, Y4. Okay, which are going to be these values. Okay. So how do you do it? You multiply 2 times 1 minus 1 times 1 plus 1 times 3 minus 5. I repeat, so this is the bias. I will shade it just to keep things clean. Okay. So now please follow me here, okay? I multiply 2 times 1 minus 1 times 1 and 1 times 3 and to whatever I get, I do subtract 5. Okay? Can you follow? This adds up to 2 minus 1, 1 plus 3 is 4 minus 5 is minus 1. That's right, minus 1. If you do the same below, I say 2 times 1 plus 1 times 1 plus 0 times 3 plus 0. That adds up to 3. Then 0 times 2 times 0 plus 1 times 1 plus 1 times 3 plus 1 adds up to 4 plus 1, 5, right? 3, 4 plus 1, 5, and then 2 times 1 plus 0 times 1 plus 1 times 3 minus 2 equaling 2 plus 3, 5 minus 2, 3. Okay, so I get here 3, 5, and 3. And because we are applying ReLU, whatever is negative will become 0. 3, 5, 3. Okay? So the output of performing a first forward cycle in our network, which is fully connected, will be 0, 3, 5, 3. And then you can go on if you want to. Okay? We just transformed an input of 2, 1, and 3 into an output of 0, 3, 5, 3, different vector. Okay? we are still not learning because we are not doing the error calculation, but you need to see how we transform the information from A to B with the weight matrix. Okay? Any questions? Questions online, please. Good. Then let's look at the next example. Is it really so clear that you don't have questions, or you're just asleep, or what's the game?
I think it's clear without the
Yeah.
questions.
Okay. Good.
Well, it's at the moment simply too much to unwrap for now, so that's why
Okay.
we're maybe not asking questions yet.
Good. You can ask the questions online on the YouTube channel. Okay. So example number 3. How do we work with a so-called hidden layer? Okay. Example number 2, example number 3. How is the hidden layer going to behave? Now imagine we have this configuration. We have 3 neurons here. We have our 4-layer perceptron, 4 neuron perceptron there, which is in the middle. And then we have an output of 2 neurons. So we go from 3 to 4. And then from 4 to 2. And here we have our input, which is 2, 1, and 3. And we are, of course, we're going to have 2 weight matrices, one W1 and one W2. Okay, so let's see how this works. So this is our W1, or better, W1 bias 1. Then we have our input values here. We know them. It's 2, 1, and 3. We have the same values we have already calculated, so I don't need to calculate them again. Minus 1, 1, 1, 0, 1, 0, 1, 1, and minus 5, 0, 1, minus 2. So, and then we have a second weight matrix. It is kind of important that you notice here we have 4 values, and here we have 3 values. One is the number of neurons input, and 1 is the number of units output. Here again, we will have number of neurons output, 2. Number of inputs, 4, right? Plus the bias. Okay? 1, 0, 1, 0, minus 1, and this would be given in the case that I asked this in the exam. 0, 1. So the bias is Shafiat. 0, 1. Okay? And the question is, what is the output here at some point? Y 1 and 2. Okay? That's the question that I could ask in the exam. So here we would have our thing before ReLU, and then we would have a hidden layer that we have actually already calculated. Because it's the same as above, okay? 0, 3, 5, 3. Just for the sake of it, I just copy it again, okay? And here we're just applying ReLU. So this is just the same as above, so I don't do it. Minus 1, 3, 5, 3. So, and the interesting part, this is the hidden output, hidden layer. And now the interesting part is, what do we do? Okay, so what do? We multiply this with this and add the bias. So 1 times 0 plus 1 times 3 minus 1 times 5 plus 0 times 3 plus 0. This adds up to 3 minus 5 minus 2 and 0 times 0 plus 0 times 3 plus 1 times 5 plus minus 1 times 3 plus 1. That's 5 minus 3, 2 plus 1, 3. Okay? So after ReLU activation function, the output goes 0, 3. Okay? Does it make sense?
Yes, it does. But I do think it's easier to understand if you would explain it with the matrix multiplication and the dimensions, you know?
Well, that's your opinion. I have other opinion.
Yeah. Okay.
Thank you for your opinion.
Yeah, I think for me, it's easier to understand if you just look on the dimensions and the matrix multiplication.
I prefer to do it visually, but it's okay. If you think it's better for you, you can do it like that.
Okay, thanks.
Yeah. Okay. questions? So now let's look at how it looks like when you do the whole thing, back propagation and the error calculation. So not only the forward step, but also the error calculation. Okay? And this is more challenging. Wait. So that was example number 3. And this is example number 4. Okay, so let's do the real thing. Feed forward and back propagation. Going back, okay? So we start with our input. How do I explain it? Best. Let me think a moment. So imagine we have performed this calculation already with 4 layers. With 3 layers, sorry. We have an input of x, 2, 1, and 3. Okay. We have a layer 1 that has let's say here these weights initialized 1 1 0 0 1 1 1 0 1 then -5 0 1 -2. If you perform the calculation as we did above, we would get to a number like, so this is the bias, just like above, and we would say we get -1, 3, 5, and 3. Okay, if we do some ReLU calculation, then we would be getting to 0, 3, 5, and 3. Our next layer would be a layer 2. Layer 2 with again some weights. We need 4, so 1, 0, -1, 1, 1, -1, 0, 1, and then 0, 3 is the bias. If we do the thing again, we get to 4, and therefore ReLU goes then to 2, 4, so no change. This is layer 2. Okay. And layer 3, gets a square. And a rectangle. So I get here again, this is the bias. It's layer 3. And the numbers are 2, 0, 1, 0, 2, 1, -1, -5, 1, and then 3, 3, -1. I don't do that because it's the same. And here we apply a something called softmax. Wait. Okay, so here we apply softmax. And the softmax does a normalization so that all values add up 1, which would be the same as saying this is a transforms into a vector of 0.5, -0.5, and 0. This is the predicted value, and this is the real value. Why we add up, we get values between 0 and 1, all the values need to add up 1 because this is a probability, okay? Saying I have a probability distribution, and then, so let's say we're trying to find out which class we are finding, so it will be this class, and we try to adjust our system so that we can predict class number 2, for instance, okay? So this is Y target. So this is the thing we are getting with the feed-forward process that we already know. So this is already filled out. Now, what do we do to do the back propagation process? Okay, going back from here to calculate this error. Okay, so what do we do? And what we do is not trivial, and you need to follow me now because it's not easy. Okay. So the first thing we do, we start in the end. Okay, we start from the end to back. Okay, to the signal again. I'm going to use another color. Habe ich nicht aufgepasst. Die Idee hier, also nochmal, Softmax ist eine Funktion, die alle negativen Werte auf 0 setzt und die positive Werte aufaddiert bzw. zwischen 0 und 1 bringt. Okay, damit Sie hier 1 aufaddieren. Deshalb haben wir hier 0,5, 0,5 und 0. Weil minus 1 wird auf 0 gemacht und 3 und 3 ergeben 0,5 jeweils. Okay, die Wahrscheinlichkeit. Es geht darum, eine Wahrscheinlichkeitsdistribution zu machen. Deshalb haben wir hier 0,5 minus 0, 0,5, 0,5 minus 1, minus 0,5 und 0 minus 0, 0. Okay? Das ist schon mal das Erste, was falsch war vorhin. So, die Idee hier ist folgendes. Ich hatte der Denkfehler war, ich muss multiplizieren, der Vektor predicted, nicht mit W3, also not with W3, but with the output, output of layer 2. This means the output of layer 2, I multiply 2 times 0.5, 2 times 0.5, so I get 1. 2 times minus 0.5, I get minus 1. 2 times 0, 0. 4 times 0.5, 2. 4 times minus 0.5, minus 2. And 4 times 0, 0. Okay? So this is the second step. The third step is to calculate, again, what we did before, the correction of this error. Okay, so I am going to do this. So this is the first step. The second step is to multiply this with W3 to get the updated weights for the next layer. So the third step, I don't like this, wait, not elegant. Here we transpose, as I said. The third step is to calculate the new weighted error that we will get into the layer 2 again. So in order to do that, we go there and we say, okay, I multiply, third step, multiply the predicted error. This is actually what we are multiplying, the predicted error. Error, layer 3, with the weight 3 matrix. Okay, and then we get a 1/2 value. So -5 times 2. 0.5 times 2 plus 0.5 times 2 plus minus 0.5 times 0 plus 0 times 1 equal, let me paint it here with colors, 0.5 times 2 minus 0.5 times 0, 0.0 times 1. Okay, and this gives a value of 1. If we do the same with the next column of the weight matrix, 0.5 times 0 plus minus 0.5 times 2 plus 0 times 1. This equals minus 1. So we get here 1 and minus 1. Okay? And this, again, we bring here. And now we repeat. Number 4, we transpose. Okay? 1 minus 1. Then we perform again the calculation. So 0 times 1 is 0. 0 times minus 1 is 0. 3 times 1 is 3. 3 times minus 1 is minus 3. 5 times 1 is 5. 5 times minus 1 is minus 5. 3 times 1 is 3, minus 3, and so on. So, again, here, in the step number 5, just like in step number 2, it's a dot product. In step number 4, we are doing a transpose of the product of the error 3 times weight 3. In step number 5, we make a dot product of error 3 times weight 3 transposed with output of layer 1. What is the dot product? Y dot product. Here I just multiply, here I multiply 2 times 0.5. Here I multiply 2 times minus 0.5. And here I multiply 2 times 0. Okay? This is the dot product. So this multiplied by this, 1. This multiplied by this, minus 1. This multiplied by this, 0, and so on. Okay? So once we have that, we need to again multiply. I take another color. Here, this, number 6, by the next, by the weight matrix of number 2. And this will give 1, 2, 3. So let me put it below. So, and now number 6 I multiply just with like step number 3, multiply the predicted error. Number 2 with weight matrix number 2. Okay, so this is error number 3, and this is error. Error number 2, and now we multiply both, and we get 1 times 1 plus minus 1 times 0. 1 times 1 plus minus 1 times 0, yielding 1. 1 times minus 1 plus minus 1 times minus 1. Yielding, wait, let me do it correctly. Yielding minus 2. Then 1 times 1 minus 1 times minus 1, yielding 2. And 1 times 0 plus minus 1 times 1 is minus 1. And this is the error number 1. We translate this again into the new world. Okay, transpose it. One minus 2 to 1. Okay, and then we get our new weight matrix okay, I'll explain it in a second. So here we multiply again, dot product, okay, so 2 minus 4, 4, 2, 1 minus 2, 2, 1, 3 minus 6, 6, 1. And this is step number 7. Okay, step number 7 is transpose of the error number 2 times weight matrix 2, and number 8 is dot product of error 2 weight matrix 2 transpose times the output or the input signal. Okay, this, what we do now, this is the result. This is the new weighted matrix 1, and this is the new bias. So we have updated the weight matrix and the bias.
Da steht da verschrieben, 3 mal 1 ist 3. Und 1 unten rechts.
3 mal 1 ist 3, ja.
Ja, da steht 1.
Ja, Entschuldigung. 3, danke. So our new weight matrix 1 of course transposed, okay? Our new weight matrix 1 goes like this. Um, 2 minus 4, 4, 2, 1 minus 2, 2, 1, 3 minus 6, 6, 3, and the bias is 1 minus 2, 2, 1. Strich, bias, strich. The next thing would be to substitute this here and do the whole thing again until we find some convergence. Okay? This is deep learning, or a multi-layer perceptron. Does it make sense? Again, I apologize for the misconception before. I had a problem in my mind.
But would we not fit the weights with a learning rate? Or does we just like multiplying the new weights E with a learning rate of, let's say, 0.1 and then fit the new?
Yeah, we can do that as well. I didn't include in this calculation the learning rate yet.
Okay.
But this is correct, yes.
Okay.
Yeah. So step number, I guess number 8 would be, no, number 9, sorry. Number 9. Number 8 was the dot product. Number 9 would be to substitute the new updated weights W1 and B1 strich. This is the way deep learning works. Okay? It goes one forward, then calculates back, then one forward, calculates back, and does this a couple times until it gets to a convergence. You say the error is smaller than, I don't know, this is the error, okay? So you say the error is smaller than 1%, and then it stops. And with this, you can calculate easy things like linear equations or quadratic equations very easily, because it approximates with lines in many directions, and then it converges. Okay? So, I repeat. We start, well, you will see it in the video, okay, but how it evolved, everything. Because to see this, I mean, if I would send you this, you would say, what the fuck, right? So, you start with the X, and then you have a weight matrix number 1, weight matrix number 2, and bias, and all the blacks, right? You calculate through ReLU, and you get to some sort of value, 0.5, 0.50, okay, after the softmax. You subtract the target, and then you get some error. This error you feed back. I'm in step number 1. You transpose and dot product it to the output of the second layer. Simultaneously, you multiply this error by the weights. Okay, so you use the error 2 times. But one is the dot product and one is not a dot product. It's just a normal matrix multiplication. That's why I don't like to use the matrix notation, just like the colleague proposed, because I think this is more visual. Okay, you just need to put things into place, but it's something that you need to decide for yourself. So you take this and you put it up. This is the result of multiplying the error of layer 3 and the weight matrix 3. You transpose it and put it up to dot product it into the second layer, and the same do the same with the weights of the. So error 2 is used again twice to multiply it with the weight matrix number 2 and to the result of number 2. The error number 1 is used again, and so on and so forth. Dot product, and then the bias calculation. Okay? This is deep learning. In the exam, I could ask you this. Okay? I could give you the input signal. I could give you 1 layer or 2 with weight matrices and biases, and then say, do me the numbers, the first feed forward, and the first back propagation. Okay? This makes sense? So if we would paint this thing, it would be something like this. In the beginning, we would have 3 inputs. Then we would have a hidden layer. with 4, then we would have another layer with 2, somewhere here, and then we would have a final layer with 3. Okay? So we would start with the values here, with the values, and everything would be connected to each other. So here we would start with everything connected to each other, right? So I don't want to do it because otherwise you would get mad. The back propagation works like this, okay? Here and here as well. So this would be that level. Then we would go to the green one. Would be that level. And then the other neuron as well. And that's what we're doing when we are multiplying the matrices, okay? And then we go to the red level, and this becomes just crazy, okay? Everybody connected to everybody else, everybody updating weights all the time, back and forth, back and forth, back and forth, super fast. You do that with so-called GPUs, graphic processing units, just like matrix multiplication. It's the same thing, the same chips that your PlayStation has. Because PlayStation is based on graphics, right? So you want a high definition graphics and you need that. Same technology to do deep learning. Actually, you can take the GPU from the PlayStation and put it and do deep learning very well. New Macs come with an automated GPU integrated. At home, I have the fastest GPU on the market. It costs around 20K. It's 80 gigabyte. I have it in the basement because there you can cool it. But if you get into the room, you have 50 degrees. So it's really not very good for the environment.
But there are also, if I remember, some SoCs, for example, now having some sort of additional neural processing units, for example, Apple Silicon, some Snapdragons, Google Tensors, and so on.
Yes, correct. That's also true, yeah. So this is the way the weights are updating. Do you have any questions? Would you like me to repeat steps?
I have a question.
Yeah.
Can you explain the softmax again?
Sure. Yeah, that was poor. Yeah. I will do it. I will explain the softmax. Wait a second. That was not very good explained. Not very well explained. I'll do it again. Wait a minute. Just let me here. Embrace it with this. Okay, so that's the thing, and then the softmax again explained. So I apologize for the confusion. Softmax explanation. So if you have values, let's say 2 minus 3 4, and then 0, and then -1, okay? And then we apply softmax in the last layer, usually, so that it gives us a distribution like a probability distribution. So all the numbers in the softmax add up to 1. Okay? Can you follow me? Hello? Hallo? Derjenige, der gefragt hat.
Yes, add up to 1. What do you mean
Yeah,
with that?
they add up to 1. So if you add up all the values here, they need to add up to 1. If you put them together and sum them up, they add up 1. So whatever negative values, like let's say -3 turns to 0. Okay? -1 turns to 0. And then 0 is of course 0. And then 2 and 4, they need to add up 1, okay? So if you put the 2 and 4, 2 plus 4, they add up 6, right? So in order for 2 and 4 to be in relation and still add up 1, you need to divide them by 6. This number adds up 1, right?
Mm-hmm.
Good. Then we have here 1/3 plus 2/3. So where you have 2, you put 1/3. And where you have 4, you put 2/3. And the rest is 0.
Okay, now it's clear. Thank you.
Okay? Yeah. Again, my bad. I didn't explain it correctly. I'm sorry. Any more questions? Graphical explanation. Good. Any more questions, please?
Ich habe eine Frage zu Schritt 3.
Ja.
Können Sie vielleicht kurz markieren, welche Werte Sie da nehmen?
Ja, genau. Schritt 3, also wir machen 0,5 mal 2 minus 0,5 mal 0, 0 mal 1. Okay? 0,5 mal 2 minus 0,5 mal 0, 0 mal 1. Du hast es auf Video, also von daher kannst du gucken. Weitere Fragen? Weitere Fragen bitte? Gut. Keine Fragen? Okay, then let's continue with the transformers, which is the heart of ChatGPT. Okay. Transformers. It's not the film Transformers, but we're talking about something else, okay? Transformers eliminate our neural networks that eliminate the need for labeled datasets. And convolution in the network. The two main mechanisms that allow for this are one, attention weighting, and two, feed forward networks, or FFN. Attention weighting is a technique by which the model learns which part of the incoming sequence needs to be focused on. Okay? It throws parts, it screens the data and recognizes what is relevant. Okay? This is important when you do text generation, because there are some words that are crucial, like verbs, nouns, adjectives, adverbs, and others that can be eliminated and you still understand what you're saying. So, a feed-forward networks are, in this context, a regular multi-layer perceptron. We know how to do it. Okay, we have seen it already today, how to calculate or how to do a feed-forward network with the pencil. Acting on a batch of data vectors. Combined feed-forward networks and attention weighting, it produces a so-called position dimensioning. Okay? So the way feed-forward network works, we have seen already. Okay, it's the above. It's multi-layer perceptron. Okay, it's done in way more capacity and a lot of things at the same time, but it's this principle. Okay, so I'm going to focus now on the attention or self-attention mechanisms. Okay. Feed-forward network mechanism, see above multi-layer perceptron or MLP. Okay, so I will not explain that again. It's relevant for the exam. You need to do it. I will ask it. So if you don't answer and you don't learn it, not my problem. Ich werde es abfragen. Ist es angekommen? Hallo? Diejenigen, die online teilnehmen, ist es angekommen?
Es ist viel zum Verarbeiten.
Wie bitte?
Es ist halt wieder viel zu verarbeiten, wie immer halt.
Ja, okay, gut. Also ist es angekommen. Ich werde es abfragen. Das heißt, wer es nicht lernt, dann verschenkt Punkte. So, what is self-attention? The attention mechanism. The transformers or the transformer architecture Entschuldigung. Architecture can be seen as a combination of two shells. Okay, so Leine wie eine Zwiebel. Okay, outer shell, the outer shell is a combination of attention weighting and a feed-forward network. Okay. The inner shell consists on a self-attention mechanism and is part of the attention weighting feature. Okay. So let's see how it works. Okay, example. The attention weight matrix A is given, okay, is obtained by fitting the input features into the architecture. This matrix tries to find the most relevant parts in the input sequence. Okay. So, how do we get it? First, we get a weight W sub Q matrix, okay, which is given. Something that we will update later with the backpropagation and so on, okay. Let's say 3 by 3. Duplicate, or no, 3 by 6, sorry. This is W sub Q, and then I have here 1, 1, 1, 1, 1, 1, 1, and then 0, 0, 0, 0, 0, 0, 0, 0. And then we have some features, some data that we are interested on. Four and then 6, right? Yeah. And then 4 here. So here some input. So, no, I don't like it. I'm gonna do it nice and neatly, otherwise we don't understand shit later. Duplicate, duplicate, here again, and then now here horizontally, one in the middle, again another, okay, so here we have some features, 1, 2, 2, 1, and then the rest 0, 0, 0, 0, then 0, 0, 1, 1, 0, 1, 2, 0, 0, 1, 0, 1. Okay. So, and this is x1, x2, x3, x4, just like we had before. We have some inputs. So here, what do? We perform a multiplication. Okay. What we're going to get is a matrix . 3 by 4. Okay, here just do matrix multiplication. Okay, 1 multiplied by 2, 1 multiplied by 0, 0, 0, 0, 0. So we get a 2 here. It's normal matrix multiplication. 0, 2, then 0, 1, 1, 1, and then 3, 2, 2, and 1. Okay. Yeah, so that we called Q1, Q2, Q3, and Q4. Is the result of multiplying our weights with the input. Okay. This is the weights. Which is we called query vector. Okay. And then we have the key vector WQ, WK, which is again is another matrix, WK times X. You get a key vector, and then you have the value matrices with X. Okay. By multiplying, sorry, this is the key vector, and then the value vector, the value weight. It's W sub V times X gives the values. So the next step is to multiply K with Q. Okay. With dot product. Then the next step is to scale or normalize each element. Usually you do that by transforming the signal minus the mean value divided by the standard deviation. And the next step is to apply softmax. To get the prediction. Afterwards, you perform a backwards propagation as in feed-forward networks. So here the key message, and I'm purposely not going into detail. The key message is you are going to learn, you are teaching your transformer to focus only on the parts that are relevant. And you do that by training weight matrices, which are weights, keys, and values. And the difference between these categories is simple. Here you have a weight matrix just as we had before in the perceptron. The keys are the different categories: verbs, adverbs, adjectives, stuff, you know? Or if you want to look at self-driving cars, you look at trees, you look at people, you look at other cars, you look, you know, the different categories. And the values are the actual values that are going to be updated on the input. Okay? So the first step is to calculate the vector of weights, the vector of keys, and the vector of values. Once you have that, you multiply them with dot product, because this is the way attention it seems to work. Then you normalize the whole thing. And then you apply softmax to decide, is it a verb, is it a noun, an adjective. In the end, you perform a backward propagation for training or error mitigation. These 7 steps is what you use to train your transformer. This is what the guys that made ChatGPT did step by step with huge amount of data to create what we have now. Okay? So ChatGPT was trained in this process, following this process, with, for instance, YouTube transcripts. People talking on YouTube, they were just translating that into text, and they were feeding ChatGPT with that. Or they were feeding ChatGPT with Twitter dialogues. Okay? This is the steps, the algorithm that takes part. The basic part is to understand the weighting thing, okay, which is a concept. It's just matrix multiplication and this stuff, the feed-forward network. This is the key bone, the heart of today's technology, this process. So make sure you understand it. Today's lecture is very important, and I will ask that in the exam. Okay? Any questions?
Können Sie nochmal runterscrollen zu diesen Keys und Values?
Yep.
Welche Werte haben die? Also WK, wie berechnen wir das? Oder?
Ja, WK ist wieder eine Matrix. Sorry. Ist wieder eine Matrix, in dem zum Beispiel ich werde halt hier Kategorie 1, Kategorie 2, Kategorie 3 haben. Und dann ist das da alles 0, außer eine. Hast du von One-Hot-Encoding gehört?
Nee.
Da transformiert man, also One-Hot-Encoding, transformiert man zum Beispiel Apfel ist 00 oder 000. Orange ist 001 und Erdbeer ist 010 und was weiß ich, Birne ist 100 und Mango ist 011. Ananas ist 101. Zitrone ist 110. Und sag mir noch eine Obst, Melone 111. Wir haben die Kategorien, deine Ks, okay? Mit Hilfe von 0 und 1 auf 3 Positionen verteilt. Und je nachdem, welche Kombination wir kriegen, reden wir von einer Kategorie oder von einer anderen. Und dadurch, diese Softmax wird mir sagen, okay, du hast jetzt, dein Ergebnis heißt, deine Prediction heißt 0,01, 0,99 und 0,0. Also, das heißt, deine Prediction wird Erdbeer wahrscheinlich sein. Verstehst du?
Ja.
So läuft es. Weitere Fragen? Selbstverständlich, wenn es euch interessiert, das war jetzt nur eine Einführung. Der Kern der Sache und das, was prüfungsrelevant ist, und wenn ihr alles andere ignorieren wollt, sind diese Beispiele, diese 4 Beispiele, okay? Da ist, wo ich was fragen kann, so was Sinn macht. Gut.